Swayamprabha. Digital India. Educated India.
Good morning again. Towards the end of the last class, we had gotten so far as to derive the dispersion relation for the simple case of one fluid flowing over another fluid that may also be moving in general. Okay. So, let us quickly recap the process of this linear instability analysis right from the beginning. The process started with first write down the governing equation and then we started with a mean flow. We also called this in several instances the unperturbed condition or more accurately the pre-perturbed condition. Okay. Then we substituted the mean flow field into the governing equations to fully establish the pressure field as well as to ensure that it is a solution to the governing equations. Okay. So, essentially this is a check where we make sure that what we had for our mean flow field does indeed satisfy the governing equations. And then we developed or introduced a small perturbation to all the flow variables, flow and interface variables, we will write it in a general way. And then we substituted the perturbed flow field into the governing equations. The next process is retain only order epsilon, which is basically linear terms, and neglect the rest. So, this gives rise to the linearized governing equations. Okay, what at this stage what we have is a set of equations that the perturbed quantities obey up to order epsilon. The perturbed quantities behave as per those equations, because you have the mean quantities are already satisfied in the governing equation. So, I will give you an example here. Say I take a function f of x and alpha is a root. If alpha is a root of the function, that means clearly f of alpha equal to 0. If I want to study the behavior of this function near alpha, what do? I define x to be equal to alpha plus y, where y is a small parameter, is a small value. Now, I can take f of x, which is equal to f of alpha plus y, to be equal to f of alpha plus f prime at alpha times y plus f double prime at alpha times y squared over 2 factorial, etc. Okay. So, since f of alpha is 0, because alpha is a root. So, this is basically where we are saying the mean field satisfies the governing equations. So, essentially what we have is f of x can be replaced by f prime alpha times y, which is a linearized form of y, which is a linearized, which is where the function has been linearized in the neighborhood of alpha. This is exactly what we have done. Now, the growth or decay of this function, or the slope of this function, let us say near alpha is basically f prime alpha. We know that from simple mathematics, right. So, this f prime alpha determining the behavior near alpha equal to 0 as far as the slope is concerned, whether the slope is positive or negative, etc. This is for a simple mathematical, for an algebraic or a transcendental function. For a differential equation, the process is exactly similar. You have the linearized governing equations that determine the growth, and what we want to find is the set of eigenvalues of those linearized differential equations, which is basically what omega is. Okay. So, this is step number 6. Step number 7, once we have the linearized equation, we went through as a matter of fact with the boundary conditions as well. So, what we have now, a complete homogeneous Okay, the next process we went through was to make the normal mode assumption. Where the flow variables are expanded in the form of the appropriate eigenfunctions. Okay, the appropriate eigenfunctions. In this case, they were sines and cosines. So, e power I k x. That was the spatial form of the eigenfunction. Okay. And then exponential in time. So, the linearized governing equations are still partial differential equations, but in x, y and time. By the time you complete step 9, you can substitute these into this gives a set of ordinary differential equations in y. So, that gives us the behavior of these quantities in y. Now, if you take any arbitrary wave that you impose on the surface, since we are dealing with a linear problem, any arbitrary wave can be decomposed into its sines and cosines. Okay, this is basic Fourier series, so to say. And since we are talking about again a linearized version of the full problem, the behavior of each sine and cosine can be superposed to yield the behavior of any arbitrary wave. Okay, this is simple. So, if I have a linear governing equation for any problem and I know the behavior due to, let us say, one forcing function, I know the behavior due to a second forcing function, the behavior due to both the forcing functions acting together is simply the summation of the solutions due to each of the two forcing functions acting individually without the other. Okay, this is so essentially what we are saying is, if I have some arbitrary wave on the free surface, I can treat that as being a superposition of several sinusoidal components, and if through this process I study how each individual sinusoidal component is going to grow, I can then end up predicting what the arbitrary wave that I started is going to look like in some period of time. Okay. So, let us complete this. So, if I say I have a set of ordinary differential equations in y, so I now know the complete solution. So, substitute the solutions for the flow variables into the boundary conditions, and what that does is it yields a dispersion relation